Welcome everyone. Today we have Dan MacKinlay, um, who is from Australia's CSIRO, um, uh, going to talk to us about this very beautifully written post that he has on opponent shaping as a model for manipulation and cooperation. And as Dan said, please interact, ask question, and if you are RL expert, do uh, do let us know your thoughts on any particular inaccuracy or on the discussion. Yeah, thank you. Thanks, Dan.
Yeah, thank you, Edmund. I guess the other thing to say there is since I'm actually a little bit uncertain about everyone's background here, there's a whole bunch of stuff in this notebook. We could take as long as we wanted to. I would be pretty keen to take it at a useful speed. So feel free to, read ahead and say, no, the next section's, crap, Dan, don't do it. Or more usefully, maybe say, you can speed up or slow down, or we can unpack anything. There's kind of a point that I'm trying to get to in this notebook, but I don't think that we'll still benefit if we don't reach that endpoint. So yeah, I think that's a kind of collective decision, what you want to do with this time, and stick up your hand or just shout, and we can stop. And I guess the other side point is I couldn't make my stylus work, so we're just going to read off the notebook. Sorry, there's no writing out equations or annotating the page or any of that fun stuff. That would be ideal, but I can't do on Zoom for inexplicable reasons. Okay, so the setting here is so yeah, we're trying to operating at the intersection of game theory and reinforcement learning here. So you may have run into both of these formalisms in different settings. I guess in particular, we're thinking about iterated game theory, where we're wondering about reasonable strategies for agents who plan to play a lot of games against each other. And games we really mean here in the sort of classical game theoretic setting. So the archetype is the prisoner's dilemma, which I've written up here just because every time you discuss game theory, you have to introduce the prisoner's dilemma. So I think this is just in the zeitgeist and everyone knows it, but just to spell it out, the classic setup here is your two people have been captured who are suspected of a crime that you've both committed, and you have to choose whether you're going to rat out the other person that you have been arrested with. And you have various, this is a game you're now playing without talking to each other, so you can't coordinate. You have to decide whether to rat out your co-conspirator or stay mum. If you say nothing, then you get off with a mild sentence. If you both rat each other out, you both go down, and it's very bad. And if one of you rats out the other, then the person who rats out the other person gets off, and the person they ratted out goes to prison. So this is like a classic coordination problem. There's lots and lots of games, but this is the one that we all imprinted on early. Yes, there's lots of work around analyzing games in various settings, and there's many sub-variants. We're caring particularly about stochastic games here. So normally you introduce the prisoner's dilemma in terms of like just what choice do you make, but we will rapidly move into the area of saying, I would like to learn a policy such that I can choose my play, my next move stochastically, maybe conditioned on some smart way on what I've observed thus far in playing this game. And I expect to play it many times, right? So I'm going to have a history of many times. I'm a serial criminal. I'm going to commit lots of crimes with Alice. And eventually, we're going to learn whether we always rat each other out or not, right? This is the essential framing. Right. So classical prisoner's dilemma is full of lovely results that are about, what strategy would be optimal to play. We don't typically have, well, historically, we haven't had learning theory here. I'll put a little asterisk in there, which is that there's actually evolutionary biology. There's a lot of learning theory for games, but it's not learning theory narrowly construed, right? So they wouldn't typically have a neural network involved in their learning process that happened in the evolutionary selection process. So as a machine learning chauvinist, I'm ignoring all that. But what we'd like to think about is how we can recover the kind of results the evolutionary biologists care about in game theory, or that the economists care about in game theory, but have some sort of model for learning in there. How can I learn what move to play next as a smart player in this game? So the natural model that we plug into there is the natural machine learning formulas that we plug into there is reinforcement learning. So reinforcement learning is, I mean, I've done a whole appendix on each of these things, right? But reinforcement learning is I would describe it as learning optimal control, because I come from a control theory background. Proper people who start up in RL don't tend to describe it that way, but that you can more or less think about it as we're going to train a model which learns to observe a history of interactions up to this point, and then learns good actions, optimal actions, such that at the conclusion of the game, depending on or the iterated game in our case, it has gotten lots of reward. It's made lots of moves that accumulate reward, where reward is something that's contingent on the particular control problem it's trying to solve. In our iterated game theory, we're usually, there's many subcategories and assumptions we can put in here. Let's just fixate on the sort of one of we're playing games against each other. We get a reward at each round. We can accumulate. I'm going to commit lots of crimes with Alice. I'm going to learn a cooperation strategy with Alice, such that over our lifetime of being criminals, we spend the minimum time in prison. So that's the dense reward setting. We're assuming we don't actually need this, but in the prisoners level setting, we're also assuming that there's independence between the games. The dependence comes through our memory of each other. We're independent in the sense that each game, conditional on the players, has an independent payoff. Although the players themselves might not be Markovian. We might have some history that conditions our future actions. Okay, so it turns out that if you take, there we go. Oh no, we're still in section 1. So if you take this reinforcement learning theory, you can. It's a relatively minor extension to extend it to encompass games. So traditionally, reinforcement learning theory is solipsistic. So I'm the only actor. I have to find a control policy that will get the optimal response out of a Markovian world. In the setting of a multi-agent reinforcement learning, which is the generalization that encompasses game theory, stuff gets weird. So the other players can also be enacting a policy. The other players could also be learning a policy, right? Like we have to consider two things in reinforcement learning. We can either be at the stage where we're updating our policy to work out what strategy we're going to play, or we can be at the fixed weight stage when we're just trying to deploy a policy in the wild that will interact well without having learned it. We may also be just trying to play the policy. These both end up being important in reinforcement learning. I'm going to brush away that distinction largely in the course of this discussion, but it's a thing to bear in mind. It's a relatively minor extension to reinforcement learning to allow that degree of state dependence, because you can extend reinforcement learning to consider state dependence, and the state can just be another player. So we can think about there's a possibility that the world that I'm observing is not stationary. I'm going to have to do something smart with my update rule to make sure that I can learn a policy in a world that is changing. And then, there's various variants of this, such that we can say, oh, look, if the world's not changing too fast, then we can show that an naive policy update eventually learns a good policy for the stationary distribution of the world, right? We can do sort of like normal stuff where we have ergodic theory-like results that allow us to learn good policies even under gradual shift. And there's more sophisticated stuff as well, about which I know nothing, so I will say nothing. Right, so that's all the machinery, and that's relatively standard. The thing that I want to get to is the problem of cooperation. So I'm interested in all this because I'm curious about what we can say about selfish cooperation in the wild. So there's actually quite a few things that I'm interested in. There's quite a few things that are probably obvious to everyone here that we might be concerned about in selfish interactions between agents, right? There's capable AI agents, but also nation states, and that kind of stuff. These are all relatively rational agents that might have to learn how to cooperate or not cooperate in the wild. And when we're undergoing Prison's dilemma type dynamics, we have this kind of problem where, I mean, if I can just import a bit of terminology secretly, we know that in the Prison's dilemma we have these various Nash equilibria, there's various viable solutions that we can play that are not what's what I'm looking for here. There's various solutions that we can converge upon, right? I can converge upon a solution where we always defect, or a solution where we always cooperate. The always defect solution means that Alice and I spend a lot of time in prison. The always cooperate one means we spend not a lot of time in prison. But there's a problem that in the iterated game playing setting, there's lots of things we can say about how viable each of these solutions are. I'm going to gloss over a lot of that because it's not really my domain. But there's this important thing that, like the stylized fact that I'd like to get at is the Axelrod tournament fact. So you have this notion that in game theory, you have lots of agents that are going to try and learn in a tournament, to go test in a tournament various strategies, how they can cooperate or affect with each other. What happens is a little bit complicated, depends on the suppositions, but over a broad range of conditions, tit for tat dominates. So always cooperate is not a great strategy for you to play because people will exploit you. Always defect is not a great strategy because life sucks for you. A strategy that is slightly smart, where you learn to punish people if they defect, but then be ready to cooperate if they're prepared to cooperate, does quite well. This is a stable strategy that the evolutionary biologist will tell us is, an evolutionarily stable strategy. Right. So,
good question, Dan. Did you say, I thought generous tit for tat was stable, whereas tit for tat was not, or something like that?
Yeah. So I'm being brutal here because I want to only discuss memory one strategies later on, but I believe you are correct. But we need an extra. Yeah,
you need long term. Yep.
Yeah. And in fact, if you want to be even more precise, we're actually caring about stochastic approximations to these, right? So we are, an annoying. For implementation reasons, we generally have RL algorithms that never assign zero mass to any action choice. So we're never going to be strict tit for tat. We can't learn a deterministic strategy. So yeah, there are definitely a couple of things I'm glossing over there. Right. Okay. So and in fact, this is also almost a Dorothy Dixer, Paul, because one of the things we learn about tit for tat per se, right, is that one reason it's not ideal is that it's not robust against noise. So if you have a bunch of agents that play tit for tat and then you give them stochastic strategies such that they occasionally defect, then you find that the population can fall into straight defection, right? So this is probably what happens. This is one reason that explains the stylized next fact, right? Which is that reinforcement learning algorithms do badly at learning tit for tat. So if you say, I'm going to train an algorithm that's going to learn a good strategy by observing past interactions with my with my prisoner's dilemma partner, then if they're learning a strategy, if we're in the training phase, then they're obviously going to try various strategies. It seems likely, well, empirically it is true that I will learn to play defect, like I learn the Grimm equilibrium. And this is maybe because we are in a learning, noisy phase of our shared history when we're trying to learn our policies. So, naive reinforcement learning applied to game theory learns to play defect. It always learns the Grimm strategy. Moloch wins. We choose to overfish, overgraze the commons. We all choose to pollute. We all choose to enter arms races, and we all go to prison. Like all the bad outcomes from cooperation dilemmas happen if we're naive reinforcement learning agents. However, there is a formalism that tries to exploit this problem, right? Because empirically, if evolution can outdo, an evolutionary strategy can outdo our reinforcement learning algorithm, we might feel that our reinforcement learning algorithm is missing something, right? It's missing a trick. So can we do better? Opponent shaping is a solution for this, right? So opponent shaping is relatively new. It's from 2018. There's a lot of variants. There's a lot of variants. I have not read all the variants. But they do. I've used the original paper as kind of a stand-in for most of them. They do seem to be the criticisms I raise of Lola seem to apply to most of them, but to varying degrees. So The notion of opponent shaping is I might try and account for, if I'm a reinforcement learning algorithm, I wish to learn a good strategy to play competitive games with another partner. If I am smarter about how I handle the non-stationarity, my model of the non-stationarity environment, then I can do better. So now we have to talk about how this is kind of a branching point in the introduction, right? So we now have to think about how we introduce this mathematically. I have just, for the sake of this blog post, I've shunted all the RL machinery to the back, which, given the audience, maybe I should be starting from all the mathematical machinery. Let's just sneak over there for a moment. The setting of reinforcement learning is that our learning algorithm is something like this. We are going to learn, we have some kind of world which has this Markovian property. We have some rewards we get from the world, which I see I changed the capitalization of, naughty Dan. All right, typos. Anyway, this Markovian world generates states of the world, and we have to choose actions to respond to the world. Right, that's the naive reinforcement learning setting. It doesn't include, it has made this Markovian assumption. We have to work out how to pack a multi-agent awareness into that model of the world and do something clever with it. The way that we actually end up doing that ends up being to introduce a little bit more machinery, which is ultimately simplifying in RL. So solving the naive expectation over all my rewards over all time is quite tedious to do in practice, and doesn't leave us with many things we can approximate and lastly with a neural network. Reinforcement learning in the neural network era tends to do stuff where we're going to approximate things like we're going to approximate partial sums over future trajectories of playing out a policy. So this is called intuitively the value function. The value function is the value that I should assume a given state has, given my beliefs about how future trajectories might roll out from that time. So you can think, if you want to think about, playing chess, a state where you are about to checkmate is a very high value state, and a state where you're about to be checkmated is a very low value state. And so you can think of some sort of Bellman type control situations. You want to, states that have high value states in their future should also be high value, and, rolling, have with high likelihood, high value states in their future should also be high value. So rolling that back, we're going to have this notion of the value of this state now based on its potential future outcomes, the potential future rewards it delivers to us. So we then have to choose, given a state, what action we need to choose to get into the next state. So we then, value our actions conditional on the state that we're into. It ends up there's kind of two reasons that we tend to break this up into the advantage function. So the advantage function is essentially the relative value of an action given a state. And this ends up being, for reasons of both Monte Carlo estimator stability and also just sort of naturalness, this ends up being what we would tend to want to estimate in practice. We want to, take the estimating the action function, the relative value of an action, as our main target. So I've just written some integrals here and not really gone into how we calculate them, but like everything's intractable, right? We can do everything by Monte Carlo. So essentially, we always want to have methods that are robust against, estimator noise and the various other horrible things that go wrong in reinforcement learning. What else do I need to excavate from here? Oh yeah, and the other key point here is our ultimate target is to learn a policy, right? So a policy is a thing which can allow us to choose actions from states. We're going to, parameterize that by some parameter vector theta, which is going to be generating the output of some neural network, which allows us to choose actions. In fact, it chooses distributions over actions, then we sample from them, right? This is still in the stochastic setting. That's all right. Now you're all RL experts, or at least as expert as I am. So what do we do then? If you want to make this go work in opponent shaping session, we need to expand we do the obvious thing. We expand our state vector to include our opponent, right? So we're going to allow our opponent's so our opponent's likely choice of next action is part of our the state that we'll get into next, right? I get a reward, but also I'm going to change what my opponent does because they are also going to get a reward. The next action determines our next joint action determines both our joint rewards. So the entry level version of that would be if I and Alice are playing Prisoner's Dilemma, and I constantly defect, then she learns, right? She should, I should learn that she will learn that I am always going to defect, right? She will draw inferences from the action that I take. So if I'm now trying to roll out my future state, I am now going to have my belief about her beliefs in that state. So we just make the vector bigger, right? It's got some sort of estimate. We're estimating the value of our rewards. We're also estimating the value of the implication of her future beliefs on the rewards that I receive. Okay. Oh, Edmund.
Question. I have a question. Should we think of this as the environment is no longer Markovian, is no longer memoryless because there are other agents, or should we just like agents are distinct, like other agents are distinct from environment?
Yeah, so formally we make the environment non-Markovian, right? We're making it sort of a partially observed Markov decision process.
Right.
Although, like this is actually a distinction between the two methods. So in the Lola, I actually assume that I can see the weights of the decision process. Right. So that is yeah. So that one's actually kind of Markovian still. But this is a pretty wild assumption in general, right? Like the notion that I could see literally inside the mind of my opponent is one of my major critiques of that method. So, yeah, as an implementation detail, we do kind of assume Markovianness for the first version of the model, but we want to get rid of that quite rapidly.
Mm-hmm. Okay. Right.
Yeah.
Thanks.
Right. And even this, I'm also as I rubber duck this at everyone here, I'm just realizing I should have actually written the update rule in here, right? So I've written the fancy variant of the opponent shaping update here without showing you the naive one. I can easily do that, right? The naive one, the value term. So my naive value is just the value of the world as I believe it will evolve without taking into account my opponent's decisions. This whole extra term here, the beta onwards, let's see if I can, nope, I can't select math markup online on my blog. Oh, well, anyway, the bit with this cross-Hessian term and so on that I'm waving my mouse cursor around that I would love to be drawing with a stylus under right now, that is essentially the deviation between the opponent shaping type RL and classic RL. So this we can kind of, I can kind of persuade myself into feeling this is intuitive, but it's not. I don't actually feel it's intuitive. So we grind through a bunch of mathematics here. This is not trivial, right? So this isn't a lot of paper, and they do a bit of work to get to this relatively simple form. But if we unpack it, what we have is this notion that, so I'm going to differentiate through my value function to get an update to my future policy. I'm also going to try and look at the value update that Alice has and then launder it into its effect on my future value function. And that involves taking cross-Hessian, having this cross-Hessian, these gradients of each of these vectors of policy parameterizations with respect to each other. That sentence was long and hopefully it made sense, right? It's, so we're differentiating a lot of things. We've definitely abandoned first order gradient descent when we do this thing. And if we, lots of things are sort of looking problematic, but let's just table those for a moment. If prepared to swallow, that's the notion, that's the update.
It's first order in terms of in terms of the gradient of Dan, right?
So each of these gradient terms is a first order gradient. But this, for example, is the gradient through me of Alice's gradient with respect to my value function. So I've made a so that is a second order term, right? That's a gradient of a gradient, but it's a cross gradient. So I mean, this might be yeah. I'll call it a gradient, a second order gradient. Yeah. So yeah, this is a painful term. But tabling the painfulness for a moment, it does the right thing. So an interesting thing about this thing where I can reason through what my opponent will learn based on what I do is capable of recovering superior outcomes from our menu of Nash equilibria in our game. For example, it can learn to cooperate. It can learn to do tit for tat. Right, so that is well known, but it hasn't been useful historically, so I've kind of ignored it. The reason is that yeah, that stuff about I was just complaining about you know, big matrices full of gradients, which is the thing that someone who does a lot of training neural networks might do. I think it's pain that's probably fairly familiar here. It's like, oh, that's not practical. It also has lots of assumptions that we don't wish to import, like that thing that I can observe the state of my opponent's weight vector parameterizing their policy with respect to their previous actions, which is a wild degree of transparency. I think that Stuart Russell does do some publications on this open source game theory, which is essentially like a very closely related assumption, I believe. But that's cool, but it's not the sort of typical environment that I at least am interested in. So ignoring that, we'd like to do better. There's a super nice paper which, to my mind, explains opponent shaping. I mean, I introduced this like history because I think that because they handball a lot of the work back to the paper basically, but the advantage alignment paper does a lot better, I think, at making this stuff seem intuitive. So their essential trick is just saying, well, let's just revisit that opponent shaping paper and see if we can tidy up the equation such that some terms we'd prefer not to deal with just vanish. And they have to introduce a couple of extra assumptions, but the result is substantially simpler, right? So this paper, we talked about the advantage function before, like the relative value of an action given a state. By targeting the advantage function and then rearranging a lot of summations, they managed to make this the notion of what opponent shaping is much simpler. So in particular, I mean, so this is kind of an arithmetical exercise, right? It's Appendix 1, I think, in Theorem 1 of the paper. We crunch through a lot of summations, and we discover that we can rewrite our learning signal in terms of advantages, and summing over our history of advantages at each step in the game. And then we can delete the troublesome dependence on our opponent's internal state. Like I still have to, there's a couple of like sly assumptions in here. I'm assuming that I can still estimate the opponent's value function with high fidelity, and they don't really explore in the paper the ways this can break. But given that assumption, I don't need to know the state any longer. I just need to know what a credible estimate of their advantage function, what a credible estimate they would have had of their advantage function is. And if I can line their estimate of the advantage function over time with my advantage function, I can then recover the opponent shaping update. So the update such that I can choose actions such that they are likely to bring us both into a situation where we're achieving superior outcomes, superior Nash equilibrium, Nash equilibria in our, for example, Prisoner's Dilemma game. So I mean, I'm kind of inclined to like not actually unpack the maths there, because I think that the statement of the theorem is kind of, I think reimagining the sums is kind of interesting, but not necessarily that insight bringing. But the reinvention of the trick in terms of that is kind of the main, yeah, that's the main payoff for me in this. It's like, oh yeah, look, we can take this ridiculous thing where I would like to, treat these advanced agents to interact favorably with each other. But now, even though they might both be billion parameter networks, I don't need to calculate a 1 billion by 1 billion gradient matrix to align their outcomes. Or I could be one of the agents, right? Like, so it's not really clear what my parameters are, but it's clear that if someone has a good estimator of my advantage function, whatever that means, then they can work out how to align with me in a cooperative interaction. Okay, so there's unpacking the prices we pay for all this, right? We get some nice short equations that look like that we can persuade ourselves are intuitive. Annoying stuff happens. Yeah, this is normal. This is normal RL stuff. The proof assumes that we know each other's advantage function, which is to say we can just calculate it. They then test it in cases where we can't do this exactly and it works still, but there's clearly going to be failure modes for this. And some other annoying stuff. So we have to specify a particular class of RL agents. These aren't controversial assumptions that we're going to learn to maximize our value, and that we're going to use in particular a softmax policy model, right? That ends up being important to make all the summations collapse telescope nicely. But yeah, this is like the modal RL model, so it's not too much of a price. But there's some philosophically interesting implications to the very first thing I mentioned, right, about the credible estimation of each other's value function. So this is kind of, for me, why I'm interested in this body of research, because I think this is the point we might start thinking about agent asymmetry. Like, what can you do if you know someone's a better value function than someone has themselves? What can you do if you know what their value function should be and what their value function is, right? Can you arbitrage the gap between those? So there's a whole worked example of the iterated prisoner's dilemma with short memory, which I think I won't walk us through that unless anyone's excited about arithmetic here. Or if anyone suddenly says, yes, I want it. Good, because it's not that exciting, right? But like it's worthwhile doing. It was very tedious to do, and I would love if someone else did it, because I think there might still be an error hiding somewhere in there. But it is an exercise in arithmetic to work out, like, if I start off with an ultra naive policy where I'm just going to choose randomly. Where I'm going to learn to choose which weights I should assign to my cooperate or defect strategy each round, and I've just learned. I mean, in this one, I'm just going to learn to cooperate or defect. I'm going to have to learn. I'm going to have to make some inference about what my opponent will learn as well. Per default, if we work for this without an opponent shaping term, what we learn is that it is rational to defect, right? My signal will push me away from defection, from cooperation. If I have a opponent shaping term and I weight it highly enough, right, there's still a free parameter which chooses how much we wish to weight our opponent's update. It's beta in here. If we weight it highly enough, then we get a positive signal. So I should a positive gradient signal, which means that I should tilt towards cooperation. Yeah, so this is actually memory less in this case. Much boring stuff.
It doesn't depend on the agent, assuming that the other agents are also Lola agent, like.
Yes. So, sorry. That's a good question. Wait, am I assuming that I'm rolling out that they're going to roll out their update? No, I don't think I do, right? In this setting, I'm only. I think that I don't assume that they will apply a Lola update to their model here. I'm saying I think because I didn't write the paper, but yeah.
In particular, it's if only one agent is doing the Lola update, knowing everyone else, and everyone else is doing the usual thing, which presumably converge to always defect.
Yeah.
Then I presume the Lola agent will also converge to defect because it would just get exploited.
Yeah, so there's two settings here. So there's the training time, and then there's the runtime one, right? So in the runtime, like if I've already fixed my policy as one that I trained using Lola, which is prepared to cooperate, then the surprising result is my opponent doesn't need to be a Lola, right? I can still find a cooperative equilibrium with Lola. If I am in the training stage where I'm running forward scenarios, and the opponent is that's a good question. What happens in that setting? So my suspicion is that I think both can obtain, right? So if we reason it through, I still have a relatively good model of my opponent. I don't think my opponent does need to, probably for some small enough beta, things could go wrong, but I think that I can still successfully learn a good strategy without requiring self-play in this setting.
It seems like a population of learners. So it's I think you're right. Like there's like two settings. One, the runtime and the training time. If during training time, there's like 100,000 usual learner, and there's only one Lola learner in there. Like that one Lola learner would just have to treat everyone else as environment.
So that seems reasonable. We also expect that so I think that also the Lola update would not work in that setting. I mean, also could imagine it wouldn't work in a few other edge cases as well, right? So if I'm playing like a 1,000,000 player game, even if we are all Lola, we would still, that advantage alignment term for any given interaction would be tiny. So we would have to have weighted our 1,000,000 way advantage alignment up to some a very large number. So so I think there's ways we can break this. I mean so I believe that they do self-play in the training phase in the paper, but that the experiment of like what happens when we're not doing self-play is interesting. I think that let's find out would be a good answer. Okay, so I think we've now just laundered a worked example and also some intuition building around the learning process. Here's some validations that the thing works. So here's the graph from the paper where they actually learn a noisy tit-for-tat algorithm. So if you can't do that, you're not playing, you're not cooperating well in the game. So good paper works. What else is there? So the non-trivial results from the paper, which there's quite a few, right? And these are just ones that I am interested in researching right now. So if you want to talk about these things more, please reach out and do stuff. So the one that's in the paper is there's something which Edmund just raised, right? Of at playtime, what do the opponent shaping algorithms do? So, I mean, there's a couple here. Oop. Cool. Something weird happened to my Bluetooth then. Am I still audible? Great. So the wow. Yep. My mouse is dead though. So so on this little table here, well, let's make it a big table. On this big table here, the top row there is our advantage alignment algorithm, and we learn that it's quite good at finding productive Nash equilibria in this competitive game. But also, kind of, you want to play against the advantage alignment algorithm, right? It's worth it for you to play against an agent that's good at finding cooperative equilibria, and it doesn't necessarily need you to cooperate that well to attain them. Like, obviously, it can't make everyone cooperate. The random agent still, randomly behaves randomly, and everyone still does relatively badly. But advantage alignment is not too badly exploited in the random game. This, by the way, is not the IPD. It's a slightly different game, but it's more or less the same.
Sorry, can you explain the the graph here. So these are different types
Oh
of
yeah,
agents.
sorry, yeah. Good point. This is a type of chart that's important in game theory, but actually maybe not be that common in the real world. So I should totally unpack that, Edmund. Thank you. So we both get payoffs. So this is a tournament game. We're going to play some number of rounds. What is it? 50 episodes of length 16. And in each of these, one of the players is running one of the algorithms to play the game. So in this one here, we have the column player as advantage alignment and the row player as advantage alignment. So in this one, we see that they have a symmetric payoff, which is what we would expect, right? They're going to behave suspiciously symmetric payoff, in fact. They are going to achieve a relatively good outcome. The more blue you are, the better you're doing. And then we can have asymmetric tournaments between algorithms that are not the same. So the row player gets the bottom left quadrant and the column player gets the top right quadrant. And as we look along there, we can see how each of the players did in each of these tournaments. So this one here is a random agent. So it's just going to toss a coin and choose to actually, I'm not quite sure what the moves are in the coin game. Yeah, it's going to randomly choose one of the strategies out of the two, which I cannot remember at this point. And it's, yeah, and so that strategy is badish, right? If it plays against, a random player against itself does meh, and against a slightly sophisticated player does terrible. AD is always defect, AC is always cooperate, MFOS, Polar, and Loca are all variants of the opponent shaping one. Actually, not sure about MFOS. Yeah, anyway, there's Polar and Loca are variants of the opponent shaping algorithm, just with different implementation details. So yeah, I mean, the really important ones here is this one here, the leftmost / topmost, and these extreme strategies on the right-hand side, which show you how we're doing against, ultra simple agents. Most important in terms of intuition building, right? If you really have a horse in the race of the best opponent shaping algorithm, you might care about the middle columns as well. But yeah, so if we look across the row though for this opponent shaping algorithm, you see that out of the non-trivial strategies, even as the opponent, I'm doing relatively well playing against advantage alignment. The only way I can do better is be playing against always cooperate, right? Like I have to hope that I find an angel in the world who, no matter what I do, will keep on, taking the fall for me. So always cooperate is essentially it's a non-attainable outcome. So we should not be too distressed that we can't beat that. And for everything else, we want to be playing against advantage alignment. So of all the credible strategies in the world, advantage alignment is the best one to choose from. So that's kind of nice, right? That tells us that even though advantage alignment was constructed in a setting where lots of sophisticated things happen in mutual agent learning, when you release it into the wild, it kind of does what you'd hope it does, right? Which is, propagate this tit-for-tat like strategy or these cooperation finding strategies. Okay.
Question. So the top left corner, those are learned. So this is playtime result.
Yeah.
And add align and LOQA is not a specific strategy, but it's a strategy learned by those algorithms. Yeah,
it's whatever strategy was learned by that algorithm. So in practice, this probably looks like tit for tat, right? Yeah. So they actually don't show the strategy of this one, and I haven't run the code. They do show the strategy for the IPD, right? So there's a couple of variants of the game, and I don't think the difference is incredibly pertinent here. And I can't remember it well enough to explain it, but they're more or less equivalent games with slightly different payoff settings. So yeah, we have this. So this is the memory one tit for tat, and this one we really do learn to how does it go? If they have just, if I can read this off, if they have at the start, I am ready to cooperate, and then if they keep on cooperating, I'm ready to cooperate. If they defect, then I wish to defect, right? To teach them a lesson. I'm not a sucker. But if they then go back to cooperating, I am prepared once again to cooperate. And if they have display defect, then I am not going to keep on cooperating and be a sucker. I'm going to keep on defecting. So that is the tit for tat strategy as a decision board, right? We can ignore the first column, right? That's just the first step, which is asymmetric with every subsequent step in the memory one case. Yeah. So I mean that in this page, it's like that's the hollow world of cooperation. So I think because there's more elaborate strategies you can imagine, right? We can imagine, testing each other periodically or something like this. Like there's many sophisticated strategies we could do, especially if we're playing richer games and had side information, that kind of stuff. But like we want to be able to solve this basic problem. So there's also some really nice, very challenging attempts to push the boundaries of this. So I am surprised they have this thing called Open Harvest Commons, which the icons are quite tiny here, but it's a tiny video game for training reinforcement learning agents. And essentially, there is an orchard that has trees that grow apples, and you can either eat the apple or not. But if you eat the apple, you get the reward. If someone else eats the apple, they get the reward. And you would like lots of reward, but also if you collectively eat too many apples, the orchard dies and there's no more apples for anyone, right? So it's a classic tragedy of the commons type game. That's quite hard, right? The actual game that they give you here, you get this screen is a bunch of blocks, and the agents see only blocks. And in fact, they only see a subset of the blocks, right? It's quite a long path of inference to recognize patterns that and discover how other agents are interacting and that kind of stuff. And then to really stress the system, only two of the algorithms, two of the agents at deploy time are trained using opponent shaping. And the surprising result here is that two opponent shaping agents in this quite punishing, quite noisy, very partial information environment can nonetheless learn to win the game of which population keeps their orchard alive the longest. So we can potentially say, well, that's really pointing in the direction of helpful tragedy of the commons-like solutions. Like if I'm trying to, with a bunch of other agents, actors, work out how not to overfish our ocean or overpollute our atmosphere or whatever, then maybe we can learn to not do that. Even if there's some nasty people, right, or just like oblivious people who don't really think about this sort of higher order learning process. Yeah, so that's super nice in my opinion. And I guess the other thing here, which is from the original paper, which I'm not sure if I said, that's quite interesting, is that they kind of try and have a crack at this question of how deeply should you model your opponent's learning strategy. And this might go back to your thing you were asking before, Edmund. So there's not a substantial gain empirically from applying higher order updates in the LOCA paper. There isn't a higher order update in the advantage alignment paper, so it's kind of like a null question in that case. But in the LOCA paper, you can say, well, I'll do my cross Hessians and see if that gets me anywhere. And it doesn't really. You get a minor increment, but it seems that there's a diminishing returns in trying to out-sophisticate your agent just by reasoning through their higher order updates. So that might say something about the symmetry there. So we also have this sort of hopeful thing to take away from that is that symmetrical agents are actually quite good with a mildly sophisticated algorithm at learning how to cooperate with each other. That's not what I would think about from reading Garrett Hardin talking about the tragedy of the commons and this kind of thing. But there's also this asymmetric setting. So this is also a research question. But there's a paper which started my interest in this area, which is not quite opponent shaping, but I would like to redo as an opponent shaping paper. And I'll just mention that briefly. It's by my colleague Amir Desfouli and co-authors. It's from 2020, and it was in PNAS. And no one read it, but it's really good, you guys. It's really good. You should totally read this paper. So they want to get at understanding how humans might fit into an asymmetric opponent shaping setting. So, they wanted to have opponent shaping so they could do this. They didn't actually have opponent shaping. So what they did was a first order approximation of that, which is they want to learn RL policies which get arbitrary outcomes from humans. Just learn how humans learn and then devise a control policy such that you get a good outcome from humans. And they, found a bunch of hapless humans on Amazon Mechanical Turk and got them to solve a bunch of learning problems, and then use that to train a surrogate model of the human learning process, and then trained an RL algorithm to learn how to get desired outcomes out of the surrogate humans. So if you want to do this over as an opponent shaping paper, you wouldn't use just an RNN. You'd use another RL algorithm and put these extra terms in there. But we can imagine that this is sort of suggesting what kind of results we'll get in this setting, right? Surprising feature of their paper is that the surrogate is sufficient to learn algorithms that control humans. Right? The RNN is sufficiently high fidelity human learning approximator that we can learn policies that will the policies that we learn trained upon those simple learners, those RNNs, transfer back to humans in the wild. So this paper then goes out there. You need a surrogate to do this in practice generally, because you usually don't want to run a million gradient steps against an actual human. Your Mechanical Turk budget's blown out of the water then. Maybe if you're Facebook, you can do this, but in general, you will want to learn using surrogates and then transfer a policy back to humans, and it just works, right? Like human beings aren't actually that sophisticated an agent when we learn in practice. So in this paper, they go out and do a whole bunch of things. Their RL agents learn some interesting stuff. They learn how to sacrifice reward so that they can mislead humans and then get more reward in the long run. They do lots of fun dynamics. For the current purposes, the major thing is they also recover this asymmetric behavior that the advantage alignment paper covers as well. So they can seed a population of interacting agents. They can seed games with agents that are designed to bring either a pro-social or anti-social outcome in there, and once again achieve that pro or anti-social outcome. So this paper is super interesting to me, because it's like, okay, well, if you know that your opponent's a chump, then at some point you can actually exploit them. And we've seen the boundaries of that in the advantage alignment paper, but we can see when we plug in the machinery to get at that in the advantage alignment paper. So this is once again into the research question zone. There's also another case which I'd like to draw your attention to, which has been troubling me, which is, okay, if I know if I know my opponent's a chump, I can exploit them, fine. If I know my opponent is equivalent capabilities to me or roughly so, then we can be assured of a mutually beneficial outcome. The case where I don't know what quality my opponent is, like how capable a learner they are, is very troubling, because that potentially leads to spirals of betrayal later on, or attempted spirals of betrayal. There are, we are both incentivized to sandbag our own capabilities for estimating our opponent's advantage function so that we can get a better deal later in a long run future. There's lots of troubling things in the unknown setting where it's not clear. So like the kind of meta incentive in that setting is distressing to me, because it suggests that if we start releasing agents to the world, we can immediately see that we have an immediate model for why and how they want to conceal their own capabilities to achieve nefarious ends. Those are the main things. So there's some other stuff that I do in here where I talk about, some annoying scaling problems that we expect to arise, which we didn't really hit in the paper, but they must exist. There's, more or less everything I just said there, but wrapped up in policy terms without any equations. And we have got 2 minutes left. So I think I'm just going to say those left as an exercise for the reader. Does anyone want to cut me down for any things I've said just there? Like, what else do you want to unpack from this little journey into this weird field?